Okay, today we're going to check out the coolest thing since sliced bread, the Posital BiSS-C Absolute Encoder Kit. This is pretty amazing. 17 bits of single turn resolution and up to 32 bits of multi-turn. Of course, we can handle up to 32 bits of single and multi-turn, so 16 bits of multi-turn is just fine. 0.1 degree accuracy, 60 millimeter diameter. That's pretty fantastic. The operating temperature, cold to pretty hot, it gets hot on the back of a motor. There's some other cool features here that we'll mention, but you can see how easy this is to adapt to your motor. So some mechanical connections, the encoder device with a dust cover and a strain relief for the connector. That's one flavor of adaptation. A critical feature here is no battery. Literally, it will do multi-turn without gears and without a battery. So this is a pretty spectacular capability. And of course, good ruggedness for industrial shock and vibration. This might actually work in some military defense style applications. So the actual encoder that I have today is one that, you may typically see a US digital Kit encoder. So the old Kit encoder would come with a sensor, a disc, mount on the back of your motor. Of course, the problem with these guys is you don't have any commutation tracks for your brushless motor. So you need an absolute encoder or you need Halls. The Maxon motor, of course, comes with Halls. We'll take a look at that in a minute. But so there's a mounting adapter plate, which goes to the shaft of the motor, and then you screw in the Kit encoder, and there's a nice dust cover with a IP65 type connector on the back. And again, harvesting the energy from the device. How do they do that? Well, they've got this little device here, which has a coil in it, and as the magnet spins, it produces a little impulse, which turns on the flash chip and allows you to store a count once per rev, so we can keep track of multi-turns even when the device is not powered. It generates its own power. Other critical features are the ability for self-calibration and to correct shaft alignment errors. So we'll take a look at the motor I have here today. Is a Maxon motor. It's a little 60-watt brushless motor. I got the 2765, which is a stock item here. It's a 48-volt motor. No load speed, 9,000 RPM. The encoder can go up to 12,000 RPM. So that's pretty good pairing. Actually, with 48 volts and about 200 RPM per volt, you're only going to go about 8,000, 9,000 RPM. So your speed torque curve on this one flattens out somewhere just below 10. So that's a couple of 2-3 amps anyways. So this Maxon motor, of course, comes with Hall sensors already wired in. I've used those to do comparisons, and you can get their Kit encoder that comes on the back. This encoder that we're going to use is the Posital Absolute, and it's not 500 counts per rev or anything wimpy like that. It's 2 to the 17, which is 131,072 counts per rev. Now the drive I'm going to use today is the Copley Accelnet Plus Micro Module. This is a new EtherCAT AEV drive. It's a small module, about less than the size of a business card. There's also an easy mounting board and an optional dust cover. So I use the easy board to get myself up and running. Interesting characteristic about the drive is that it can do dual absolute. So we can have two Biss-C encoders, one on the load, one on the motor. Today we have one on the motor. And then for wiring the Biss-C, it's pretty simple. You power it with 5 volts. You get the clock out to the encoder, and then you get data back. This is a unidirectional form of communication to clock and get data. But this Biss-C has a bidirectional spec, so you could write down the encoder. We don't need to do that with this one. This will work on a unidirectional, but you can see that the clock comes out on XX0 and the data comes back on AA0. Other drives, it's S and S0, but the A and A0 is now the bidirectional. All right, so we'll take a quick look at the note that comes with the encoder. Energy harvesting, 32-bit, 17-bit, multi-turn, no battery, self-calibrating. You can quite a range of voltage there, so 5 volts is safe for that. 100 kilohertz to 10 megahertz, so our standard 4 megahertz for the Biss-C will work just fine. So in several microseconds we get the position data, and a maximal permissible speed of 12,000 RPM. That's pretty good. This one has, of course, 16 bits of multi-turn, accuracy of less than 12-bit at 0.087 degrees. I think we may be doing a little better than that, actually, for the single turn. We'll take a look at that with using the Copley drive. And then, of course, the wiring diagram, you know, ground and +5 on BCC, clock signals, and then the data signals. So those are the pinouts that you have for wiring. And you can see there's a cable option for this. The package that I'm using is a circular one, but the encoder's small. The overall diameter, less than 50 millimeters, even for the dust cover and the mounting of the dust cover. The inner diameter of the device is, again, like 35 millimeters or something. So there's some mechanical specifications for mounting and some cable options. So just to go over a little bit again, we've got the AEV Accelnet Micro Module here mounted to the Easy board. I've got that hooked up to the Maxon motor with the Posital Absolute. The feedback device goes off to the drive, the motor power wires. Here's an example like a Renko on the back of a little size 17 motor, some other adapter kit. These are just your basic incremental. This one's incremental with commutation tracks, and this one is just purely incremental. So that's insufficient for commutating a brushless motor. This one is very sufficient for brushless motor, but it's not absolute. It's only, you know, like several thousand counts. This has 131,070 counts per rev. And we'll take a look at the basic setup. So using the Copley CME2 version 8.0, I'm able to talk to the AEV, the new Accelnet Micro panel drive, and we can select the encoder type, and we set the bits. The bits is 17 bits of single turn, 131.72, and the number of revs is 2 to the 16, which works out to 65536. There's no silly alignment bits with these guys. You know, they follow the spec really good. And there's no unusual configurations. It's just the default configuration of the Biss-C. Nobody took liberty and changed the spec to do whatever they want. So this one is a good one. For mounting the encoder, you can of course move it to the 0 position and then install the feedback device. So to get this, you can use the manual phase screen and align the motor shaft by hooking up power to a pair of wires and pulling it to a pole position, and then attaching the encoder to the 0 position. That way they come out consistently and all the same. So let's take a move here and see what we get with this fancy encoder. We'll do a little analysis on the feedback here. So what we can see is accelerating in magenta to a velocity of 8,000 RPM and then decelerating to a stop. The following error before you move is near zero, increases a bit when you're accelerating and stabilizing. And while you're running, there's a little bit of ripple here. We'll take a look at that. And then as you decel, again, the following error, and then settle to steady state. This error while we're running has to do with the motor's detent. So based on the speed, you'll see a different frequency here. There's a little cog in the motor, and we're getting plus or minus 100 counts or so of error while we're moving. So this is actually still pretty good for scanning. 100 out of 131,000 is not very much error. And we'll take a look at the resolution and the accuracies. Actually, this will just show us the resolution here. You can see when we hit the steady state, we're at 0 counts, plus or minus 1 or 2 counts. This would have to do probably with signal-to-noise ratios and accuracies in the encoder. So if you knock off a couple of bits from the resolution of 17 bits, you're probably down to 15 bits of accuracy. Well, at least accurate resolution. The accuracy should probably be measured external to the device here. So you'll notice that I am hitting my speed limit here. I get a little voltage limit warning here. During acceleration is when you use the most current. But otherwise, you get some back EMF and some field-oriented control here with the D and Q vectors. I do want to note that, how are we able to get it so good with the Copley? There's two things. One, the motor manufacturer may not tell you to make sure the case of the motor is connected to earth. Don't mount to an anodized surface. You don't get good conductivity. So I brought earth to the case of my motor. I've tuned the AEV in such a way that I'm critically damped. I use my intuition to tune, and maybe a quantum computer could do some better than human tuning in the future, but for now, I'd say, tuning it just softly and nicely is a good way to tune. And if you take a look at the rise time here of the square waves, right now I'm measuring U and V output, and it's center weighted, so it's always switching. And we have, looks like about 300, 400 nanoseconds of rise time, but that's not how you measure rise time. You do the 10 to 90%. So when the competitor says they've got 40 nanoseconds, they're not measuring the 10 to 90% here. I get a rise time of about 135 microsecond, and this is at full speed. So this is the switching edge, low energy, low noise. That's really good for an encoder device that has analog signals that it's measuring. This gives Copley the advantage over the competitors for more accuracy, less noise, emissions, and immunity. Of course, I'm more than 10 miles from home and have a computer bag, so I guess I'm an expert on emissions and immunity, but there's a lot that goes into it, and maybe in the future we'll talk some more about that. Hey, thanks for watching.